let's go. Okay, so
All right.
today is chapter 11 and 12. Chapter
Hello, future
12 is
people.
where the whole insanity comes into place again from that we were talking about in chapter 10. But we're gonna have
Yeah.
a relax chapter, which is chapter 11. And then in chapter 11, we're gonna talk about the difference between declarative programming and imperative programming. Um, so something to keep in mind is this sentence right here. Um, so there are, roughly speaking, two ways of doing computation, right? By telling the computer what to do, and by telling it how to do it. And we're going to explore with an analogy how can we have an intuition between declarative and imperative. And the declarative is about telling what to do, and the imperative is telling it how to do it, right?
Yeah.
Um, so then we have a call by needs mention, because what basically composition is saying that something needs to happen before something else. Um, so there are use cases in this in making a compiler and stuff like that. And then we go to the question: when we face a problem, do we always have the choice between declarative and imperative ways of solving it? Um, so then we go to another domain, which is uh, domain of physics, to try to understand this dichotomy that also happens in there apparently. So there are two ways of expressing most laws of physics. One of them uses local or infinitesimal considerations, right? So it's very like short. That's why we're calling it local. So between one state of the system and the next one, it's very close. Um, we look at the state of a system around a small neighborhood and predict how it would evolve within the next instant of time. This is usually expressed using differential equations, very classic. Um,
There's kind of an interesting parallel here with operational semantics, actually, of small step versus big step operational semantic in particular. That's
mm,
something that this reminded me of a little bit.
hmm Well, but what exactly do you call small and large steps in that?
Uh, Okay, so operational semantics is a particular way to define the execution
Yep,
of computational calculus,
yep.
right? The difference between them is in small step semantics, you specify, okay, here's an algorithm to go from the current state of the computation to the next one, and then you apply this repeatedly until you're done, right?
Yep.
In big step, you say, okay, here's the current state. I know all the rules of the calculus. Let me figure out how to go directly to the final state in a single step. That's why it's called big step.
Oh, okay. I see. I see. And then there's the observation. Notice how this resembles imperative thinking. You reach the final solution by following a sequence of smaller steps, each one depending on the result of the previous one. Um, and that's very interesting. Then we have some examples, such as Newton's laws of, no of motion. Um, um, And then we go to the other approach. And the other approach is called global or holistic, right? So we look at the initial and the final state of the system and calculate a trajectory that connects them by minimizing a certain functional. Which, yeah, this part I forgot about it. So the minimizing is kind of interesting. The simplest example is Fermat's principle of least time. Uh, yeah, so this is basically like I know where I am, I know where I want to be. Let's establish a trajectory. How can I go from one to the other? That's how the global approach does things, right? And then there's another
Right.
example here from the refraction of how light works. And then he says all of classical mechanics can be derived from the principle of least action. The action can be calculated for any trajectory by integrating this, which is the difference between this and that. Yeah, this is potential energy things. I remember this from university. Yep. Uh, so when we can use the local picture of doing things, in which things happen sequentially in small increments, or we can use a global one, which is where we declare the initial and final conditions, and everything in between just follows. Um, so there is a comment that the global approach can also, there is also an immediate programming example. Um, so then there's a very interesting paragraph here. The biggest difference between the local and the global approach is in their treatment of space and time. The local approach embraces the immediate gratification of here and now, whereas the global approach takes a long-term static view, as if the future had already been preordained, and we are only analyzing the properties of some eternal universe. So that's why I had the notion of any. That's why it correlates with the thing about the next time delta, right? So we're using an infinitesimal thing. So you are like you are a molecule of water, like of hydrogen or something, and you instead of understanding the crash of a wave on the beach by the water being some like uh, conglomerate of water and you just analyze that, the imperative approach will try to understand each hydrogen of that. It will try to go from what is happening with all of those guys in instant t and what's going to happen in t plus delta t. So it's a more like a very local, very like specific way of doing that. And the global approach is more about like we have this state and this other state. What is the trajectory between those two? It's more like high level.
Yeah.
So then we have the example of FRP, basically establishing that it's a global way of doing reactive programming. Um, and he says, I would argue that category theory encourages a global approach and therefore supports declarative programming. I think it's very fair to say that category theory encourages a global approach, and the reason why is because we are so non-focused on how each individual thing moves across some axis that we have the privilege of not even looking at them.
Yeah, we just know that the objects are distinct and like we don't care about what they are exactly. We only care about the morphisms that connect
Yeah,
them.
what are the
That's all.
relationship? How can we talk about them without talking about them? That's kind
That's very zen.
of. So yeah, all we have is abstract objects and abstract connections between them. That's exactly what we just said. If you get from A to B through a series of steps, you can also get in one leap. Um, and then the major
And that,
tool of category theory is universal construction, which is basically describing objects not by themselves but by their relationship with shifts, which are nomorphisms.
yeah, this is actually like a nice chapter, but also, I mean, it's the first chapter of part two of the book, so you can't really just drop you off a cliff right away.
I don't know about
uh,
that. I have a very strong feeling that we could just go to 12 straight up, and this is just for relaxation because your mind is melted because of 10.
yeah, that seems fair, actually.
Um, and then he finishes saying whether used directly or not, categorical definitions justify pre-existing programming constructs and give rise to new ones. More importantly, category theory provides a meta language for reasoning about computer programs at the declarative level. It also encourages reasoning about problem specification before it can cast into code. So I think that it's important. This is the end, right? Yeah, then we're going to
This
go to
is the
12.
end.
I want to finish 11 saying a thing. So it's very important to understand, right, that not everything, not everything will be of some specific mathematical domain, such as category theory. You will be able to immediately follow within a one-to-one mapping in some programming language code. But and then the question is, why are we studying this if there is no mapping necessarily? And the reason is very explicitly stated here because we can try to we can try to pick a problem, and if you're having a difficult time under trying to implement it in some programming language constructs, we can switch the domain to something else, try to solve it in there, and after we have a very solid understanding on how to solve it in there, then we can transpose it again to the domain of implementation. This is a very common thing that we do in like electrical engineering, because if you have a signal, everybody knows that there are two domains in which a signal can be understood and manipulated. We have the time domain and the frequency domain. And it's very common that if you want to do some operation on top of your signal, you know you're gonna have an easier time doing that if you transpose one from one domain to the other and then going back to the original one. And this is kind of the thing here. So first point is you may have an easier time mapping the problem in categorical terms, solving it, and then moving it back to the implementation domain. And there is also the other, this second part, which is the give rise to new ones, which is what if there is a thing that we discover in categorical terms that are very useful uh, when using those terms. Are are there representatives of those terms in the other guy in the programming language? So maybe we can try to discover new programming language constructs because we have unmatched ones in the categorical definition set. So that's very important, because if you don't have this in mind, you're going to have a very hard time justifying and studying these type of things. Not
It's all gonna
everything.
sound like, yeah, it's just gonna sound like abstract nonsense.
Yeah. So that's the. Although I still think there's value in studying it just for the sake of understanding this methodology of thinking about things as a person, not even as a programmer. If you want to have an utilitarian motivation to do it, those are the two that it's being listed here, which I think it's very fair. So cool. So now back to the torture.
Just one last thing. There's a link to a paper like in the last paragraph. Well,
Yeah, this one.
uh, yeah, I actually took a quick look at it. I didn't go too deeply into it, but it looks interesting. So I'll probably try to check it out on my own time.
Yeah, this is being referenced as the programming language in categorical definitions, I believe.
Yeah,
Yeah, yeah, maybe it's worth a look to check it out. Okay,
it's
uh,
chapter 12.
chapter
Oh
12.
boy.
Oh boy. Okay, so chapter 12 is basically about how can we use what we have just learned to describe things more precisely. That's what we want to do here. Um, and then this actually pushes a question, like this raises a question that is very interesting, which is how do we know we need to stop?
Maybe we don't.
Because if you read it, it's gonna see that Oh, do you remember product? Oh, yeah, part of this is the drawing of it. That's cool. But you remember part of what we use to describe it. And then the construction of a product starts with the selection of two objects A and B, whose product we want to construct. Cool, that you remember that. But then it comes the question, but what does it mean to say select objects? So it's the kind of thing that we are using loose language. We're gonna use we use loosely defined terms to do something. And now that we have all this baggage that we just learned in 10 in 11 chapters, can we use more less loosely defined terminology? And the answer is
Yeah,
yes, of course. But that's the problem because now you need to like the problem is there's you I don't know about you, but I didn't develop very strong intuitions about the whole natural transformations thing. And what we are doing, we are when you do this, you are packing more stuff into it. Now the intuition of selection needs to be in correlated with natural transformations after this chapter.
yeah. This is like it's basically saying, okay, how precise can we be exactly? And it turns out we can be quite a bit more precise than we were originally.
Yeah,
And apparently, there's like a bit of a spoiler in the text here because it says, "Oh, if we had can extensions, but we don't yet." So, like, yeah, there's more stuff to come to be even more precise later, I guess.
yeah,
Um,
yeah. But let's go through this example here of what does it mean to say select objects. So we can abstract this pattern of selection into a category, a very simple category, which is a category that we're going to call true for some reason. I think it's a bad name, but that's okay. It
it's
contains
two because yeah, there are two objects, and that's all.
that's very lack of creativity in my books, but okay. It contains two objects, one and two, and no more functions other than the two obligatory identities.
Now
Right?
those are bad names. They should have been called 0 and 1 actually.
that's that's a very very you joke. Okay. Now we can rephrase the selection of two objects in C as the act of defining a functor D from the category 2 to C. So what we are doing, let's remember, a functor is a mapping between categories. We have these three objects in the category C. We are creating another category 2, and we are saying that the act of select is in fact the act of defining a functor. This functor map objects to objects as expected. So its image is just two objects, right? So there's maybe some collapsing going on, but it's going to be mapping to two objects at most. And it also
Yep.
maps morphisms. In this case, it simply maps identity morphisms to identity morphisms. I don't understand what he's calling it identity though, because none of these, there's no identity drawn in this drawing here.
Yeah, they're not wrong, but like it's basically a rule of category theory that there's always an identity morphism.
No, I remember that, but I think it's kind of confusing to him to just mention the identities where is P and where is Q. That's kind of weird.
Oh, yeah, no, P and Q are like, yeah, they are not the identities. They are
Yeah,
something else
I
separate.
that I got it, but where are they in this process that he's describing?
Not not shown, not pictured, I guess would be the cliche way of phrasing it.
Uh, yeah, so we are basically this is the functor, right? So this is the functors, these arrows. Here are the objects of
uh,
this category 2, and here are the objects of the category C.
yeah, it's actually more like that. The functor is the two arrows together because it maps a category to another, right?
Yeah, yeah. So, yeah, that's correct. But we need to remember that it can be more than one functor between two categories, right?
Right.
Let's continue. Next step is the definition of a product is a selection of the candidate object C. We need to rephrase that. And indeed, Well, then there's what Marinho said, which is that if we had can extensions, but we don't. A constant functor delta from the same category 2 to C. So delta is this guy that goes from
From 1 and 2 to C, well, small c,
1 and 2 to C,
to little c, in
to little
fact.
c, yes. The selection of C in capital C can be done with the functor delta C. Remember, delta C maps all objects into small c and all morphisms to identity of C. So now we have two functors, right? We have the original ones, the original one that talks about the objects A and B, and we have a constant functor that maps all the objects to the
Myself, in fact.
uh, myself. Oh, to C.
Yes, to
Yeah,
little c.
little c. Um,
That was
and
a
then now
plan.
it comes the question, right? If we have two functors, we know that there is a way to bridge functors now because of chapter 10. So that's the next natural question. Haha.
Yeah, natural transformations. Okay, we have two functors. Is there a natural transformation between them?
Yeah.
Um,
So this seems very complicated, but this part I think it's very straightforward. So let's go. So we have delta C and D going between category 2 and category C. So are there any natural transformations? Fine until then. Um, so since there are only two objects in true, natural transformation will have two components. Object 1 in true is mapped to C by
delta c.
delta C and to A by D. That it is. Uh, so the component of the oh, that's what I just read. We can call it P, right? We're gonna call the component of the natural transformation between delta C and D at 1 as a morphism from C to A. Oh, okay. No, that's still fine. That is what we said. I think in chapter 10 even, that you can see natural transformations between morphisms between objects in a different lenses of stuff. So that's going to
Yeah.
be P. So P is being born out of the natural transformation between functors that go into the objects. Right?
Yeah, it's like a natural transformation has many, many components. It's actually more like a bundle of morphisms if you go down to that level. And one of the components, the one that goes from little c to A, is the one that we called P back when we were defining products originally.
Yeah. We can do the same kind of stuff to
That
to
Q.
Q, and that will connect C to B, right? And these are the two projections that we use in the original definition of the product. So that makes sense. So that's the thing. Instead of talking about selecting objects and projections, we can just talk about picking functors and natural transformations. And again, you need to wrap your mind around this suggestion. It's not going to be easy at first because, well, you need to actually have pretty okay, decent understanding of these abstractions. And here's the drawing. So P and Q, they are being born. Yeah, they are being born by the natural transformations between this functor and this other functor. The functor
Mm,
going up, which is delta, and the functor going down, which is D.
Yep. Yeah.
Yeah, yeah, that's very fine.
And now comes what mathematicians always do, which is let's generalize this to more stuff.
Yeah, so we're gonna try to generalize this a little bit further on the line. So a generalization of this construction to categories other than true, so other than the simple category of true objects that we just used, will impose naturality conditions on the transformation between delta C and D.
Yeah, because the arrow diagrams have to commute, right? They always
Yes,
have to. Otherwise, it's
yes.
not really a natural transformation.
We call such a transformation a cone because of the image of delta is the apex of a cone slash pyramid whose sides are formed by contour components of the natural transformation. That's a lot to read. That's very a lot to read. So
Yeah, basically,
let's try to use the
yeah,
drawing as the guide here.
yeah, basically, you see the drawing, you see the right side of the drawing. Just picture that in 3D, and
I don't think
there's your just.
that's I want to go from first principle. So what are those arrows? Let's just start by that. So you have three objects. You have three objects in this specific category here. We only had two in the other one, but now we have three. So there is a
And this
constant
one's
functor called delta that picks all the objects in the first category of the left and collapse them into a single one of the other category.
yep,
That's why this is the apex, because it's going to be the top of the cone slash pyramid. Then the definition of the product, which is the green, blue, and red, it follows, right? It follows from as being the natural transformations between the functors.
right. And the second natural transformation just gives you the base of the pyramid, right? Because it maps those three objects and also the morphisms between them to these three other objects with morphisms between them on in C, in big C.
Wait, are you saying that this is a natural transformation as well, or this one down here?
Yeah, those three arrows that go from the triangle on the left to the base of the pyramid, that's another natural transformation. And here it's called, well, it's actually a functor, right? It's
Oh,
called
that is
B.
a
And
functor.
then
That's what I was about to ask. This is a functor, not a natural transformation. The natural transformations are always vertical.
yeah, and the natural transformation gives you the sides of the cone
Yeah,
slash pyramid.
yeah. So that's it. Again, nothing too crazy. That's still fine. It's still a little bit to wrap your mind around, but it's kind of fine. So in general, to build a cone, we start with a category. Yeah, it's going to explain basically this process that we just described. Natularity requires that all triangles commute, as expected, right? And if you don't remember what commute means that if you have two somethings, two dots, and there is more than one path that you can go from one to the other, these paths they need to be equivalent among themselves. That's what that means. Um,
Yeah.
yep. Okay, so this is are the components of the natural transformation. So what do we have in here?
We went back to the product case,
We went back to the product.
except now there's a morphism between the two components.
Yeah,
So,
there's F, and in the functor the F is lifting that.
yep.
And then, so that's one cone, right? So this is one, this is another. But we want the general case. What's the picture of the general case?
The universal cone.
Just like we picked a universal object. So we may define a category of cones, right? So that's very confusing. But imagine for a moment that all you have listed all the possible initial I categories and the C categories. And then you create in your mind all the possible cones that you can derive out of that. Now treat each cone as an object. All this monstrosity as an object. Um, Objects in that category are cones. Not every object C in C can be an apex of a cone though, because there may be no natural transformations between. That is true. That is true. Actually, not really though. Let me think for a moment. I don't think that I don't follow this. Because to have C as the apex of the cone, you only need to have delta C. You don't need to have the natural transformations between it and D.
No, you do need them
No,
because
you
that's
need
what
to
gives
create
you
the
the.
cone. not the apex of it.
But you can't have an apex without a cone. Otherwise, it's just a single object.
Do you agree that if you are a cone, you have an apex, right?
Yes.
So what I'm saying is that you can have an apex and still not have, like, it's the whole necessary versus sufficient thing. To be a cone, it's necessary to have an apex, but having only the apex is not sufficient to classify yourself as a cone. But if you are a cone, you will 100% have an apex, which means, in my understanding, that to have the apex will always be there if you have delta C. You may not have the rest of the cone because that implies that you need to have the natural transformations between the functors.
But if you don't have the rest of the cone, do you really have an apex of a cone that doesn't exist?
To me, that makes sense though, because if there is a chance of having a cone there, we already know one of its parts. Do you agree on that?
Well, yeah, you could call it a candidate apex, but it's not really an apex of a cone if there's no cone.
Okay, I can settle for candidate, but I think this could be rephrased a little bit better though. Not every object C can be an apex of. Oh, I think this is where I got confused. It's of a cone, not of the cone. Hmm? I think that's what it's saying what you said. I understand now. To make it a category, you also need to define morphisms between cones. So what the heck are those? What the heck are those though? Huh? Because morphisms between objects is just morphisms. Morphisms between categories are functors, and morphisms between functors are natural transformations. What the heck is morphisms between cones?
Maybe
I
they
have
don't
no
have a
idea.
special name, they're just called morphisms.
That these would be fully determined by morphisms between their apexes. That's very interesting. Why? You don't need to map all of this nonsense? Only the apex is enough? Huh. That's weird. Do you know
Oh,
why?
right. It's because I think I know why actually. It's because of the naturality condition, right? Because we're dealing with natural transformations to define the cones. That means that you can't really choose the morphisms from the apex to the rest of the cone, to the base, right? But that also implies
Oh,
that
I
there's,
see. So you're using naturality to say once you pick one, you have picked it all.
yeah, and then if you have morphisms between the apices, then, well, the bases are constructed by naturality. So naturally, that means that whatever
Once you pick
morphisms,
the apex, you are done. Or you
yeah,
pick it all, or you don't pick anything.
yeah, yeah,
I see. But not just any morphism will do. Remember that in our construction of product, we impose the condition that the morphisms between candidate objects must be common factors for the projection. So now we go all the way back to the whatever chapter we talked about products. This is 100% product in here.
yep.
And there are various constraints about this, but I remember two of them, which is that M needs to be unique, and you need to be able to factor P prime and Q prime using P and Q and M. That's what
Yep.
I remember. And this comes the thing that I got. This is where I got lost reading the chapter. This
Okay.
condition translates, in a general case, to the condition that triangles whose one side is the factorization morphism all commute. And then there's this thing with the legend. The commuting triangle connecting two cones with the factorizing morphism H. Here, the lower cone is the universal one with lim D as the apex. What the heck is this? What the heck is happening here?
Uh, well, basically, if you have two cones, right?
Where are they?
And okay, let's call one of them, let's name them by the apex, right? Because we
Sure.
just established that the apex kind of forces the issue about the base.
Yeah.
So those two cones, they have a common base, right?
Which is this down
And
here?
there's the one down there, and there's a morphism from one to the other, right? Which is age.
There is a morphism between one and the other. What is the? Tell me the geometry of one of them.
The geometry of one of them.
Yeah. Yeah. So how are you seeing it? Because you said that the base is down here, right?
Yeah, the base is those three objects with the morphisms at the bottom.
Sure.
Then you have the that lim D that points the object in the middle. That's the, let's call it the lower cone, right?
Oh, I,
And
I
there
see
there's
him. I see it. I see it here.
and there's a higher cone above it, which is the one with the apex at C. And there's
Oh,
a
so it's
morphism
not like
age.
they are this. It's more like they are this.
Yeah, they're kind of stacked on top of each other.
Ah, I see. I see. Now I see the problem. I was kind of trying to see it as like this.
Yeah, no, this is, we left the realm of 2D. This is fully three-dimensional now.
No, but I was kind of trying to understand it in 3D. Like they are just the apexes are like they are like twin things, like twin brother things. You know, the base is the same, but they diverge on the top.
Yeah, it's like if you have two pointy hats and you stack one hat on top of the other. That's kind of what's going on here.
Exactly. I was completely off. This is not it. This is one top on top of the other. Now I see the picture. Now let's see its meaning.
Well, the meaning is, once you get the picture in your head, the meaning is actually not that difficult because this is basically saying, okay, you have two cones, right? And there's a morphism between them, that age going downwards,
Wait a
and they share
moment.
a base.
Isn't this then just a rotation on top of this?
Uh, well, that's basically like, okay, you took the picture on the top, you added a third object at the bottom, at the base,
Yeah.
added the missing projections, and then you just connected them with some additional
And you
morphisms.
rename
That's,
M to H for some random reason.
yes, for some random reason. Um, and basically, the meaning is that, okay, we just established about the whole naturality thing, right? With the morphisms between the apices implying connections to the morphisms at the base. Um, and we're basically saying, okay, if there's an age between two cones that share the same base, then naturality follows from, the each triangle that goes from C to the base with age as a second side, and then the P and Q, right, which are not labeled at the bottom picture for some reason.
Yeah, yeah, no, it's a complete misstep. It's a 100% misstep. If the A and the B and the whatever and then the P and the Q, if they were here, I think the image would be much more straightforward.
Yes,
I have another question though. As far as I remember, if all of this holds, we call this as the product, right? C.
yes,
So the generalization of a product in n dimensions, we call this lim D. Huh.
yeah, because like the product was defined as the in some sense it was based on the idea of um, oh, we're going to get to that in the next paragraph, but it's basically in some sense kind of like a terminal object if you consider the all the factorizing arrow morphisms, right?
Mm-hmm.
And this is kind of the same thing, except there's more moving parts to it. And they call it lim D because we're going to get to that word later, but it's the limit of the diagram. And the diagram is D because, or it's a diagram. It starts with the letter D, so let's just pick the first letter. That's what we do in math, right?
Sure. So we take those factorizing morphisms as the morphisms non category of cones. It's easy to check that those morphisms need compose and that the identity morphism is a factorizing morphism as well. So we did identify that we actually have a category of cones. And now we go to the whole terminal object thing. So we can define it. We can define the universal cone as the terminal object or in the category of cones. So for those, or at least for myself, the terminal object is the one that we have only morphisms going into it, right?
Yes.
We only have we have all other objects pointing to it, connected to it.
Yes. That's equivalent to saying every other cone that is like not universal has a morphism to the universal one.
This is yeah. So let's see if my picture is correct. So imagine that you have now that we establish that these cones are one on top of the other in 3D. Is it
Yeah.
fair to say that imagine an infinite stack of those? All of those are pointing to limb D.
Doesn't even need to be a stack. You can have like two like a two two objects at the same height as C, but like going different ways, and they both have arrows going to the limb D. That could happen.
Okay, so it's
I'm
just a
not sure.
coincidence that in this particular case C is on top of limb D.
Um, it's not really a coincidence in the sense that okay, if limb D is really the terminal object, then yes, every other cone that has the same base will have like you can stack it on top of it. But the point is that they don't have to form like a strict tower. Um, they can be more like how can I say this?
They can be separate. That's what we're trying to say.
Yeah, like there could be another like let's call it C prime that's at the same height as C, and it also points to limb D, and there may or may not be some relation between C and C prime, but like they are not really on top of each other. They are both on top of limb D.
Hmm. We call this cone the universal limit of the diagram. We see a left arrow pointing towards I under the limb sign. Yeah, this makes sense because we just established that we can describe the entirety of the cone just by the apex, using naturality as the chain between them.
Yes, yes, indeed.
The intuition is that the limit embodies the properties of the whole diagram in a single object. That's very profound, man. The limit of our true object diagram is the product of the two objects. Yeah, but in that sense, it kind of does because if product is about having a little bit of everybody, that means that the universal thing of all the possible things will be able to describe everything. So, yeah, I guess.
Yeah, in that sense, if you want to bring this to a more concrete level, you can okay, suppose you have like a giant product um with like seven things in it. You could build that and it will be equal up to isomorphism to just a nesting of pairs
Yeah.
until we reach seven items, right?
Mhm. Okay, we need to speed this up because we have 17 minutes and we have until 12.5, I believe. So let's go.
Okay.
Uh, we're not only dealing with one cone, but with the whole collection. If the limit exists, one of those cones is the universal one. For every cone, we have a unique factorizing morphism that maps to its apex. We have seen this before. Given any cone, there is a unique morphism of a special kind. We have a mapping of cones to special morphisms, and it's a one-to-one mapping. We have a mapping of cones to special morphisms.
Yeah, the morphism that goes to the terminal object, the lim D.
Yeah, but saying it like this, that we have a mapping between, it's kind of weird. because it's basically saying there is a morphism between there's morphism between each cone and its special morphism. I don't think that follows, right? I'm reading this wrong.
Yes, when it says special morphism, it's actually referring to the unique morphism that goes from that particular cone to the universal one.
Yeah, but there's no morphism between those. There's no like, here's a cone, here's the universal one. There's a morphism here. But the way that it's written, I'm imagining there is a morphism between the cone and its morphism to the special one. There's another way of doing this.
I mean, I suppose you could create a category where you can have morphisms as objects.
No, we don't need that.
And
That's why we have the home set.
well, yeah, we don't. I mean, you could make a two category, I guess. We saw that in chapter 10, right? Um, but yeah, there it's basically just saying, yeah, there's a unique morphism to the terminal cone, so there's a one-to-one mapping. That's kind of the bottom line here.
Hmm. Okay, so so this home set is all the morphisms between C and lim D.
Yes, for some C going to the lim-d, basically.
The other members of this home set are less fortunate in the sense that they don't factorize the maps of the two cones. I don't know if I understood that. The other members of this home set are less fortunate in the sense that they don't factorize the mapping of the two cones.
Basically, there can be like other morphisms from C to lim-d that actually aren't the um, that actually aren't the one that factorizes it, like the one.
Oh, okay. So we want to be let's he says here be able to pick the special one.
Yes, we want to find the special one. Exactly.
What are the functors that are related by this transformation? One functor is the mapping of C to the set to the home set. It's a
Yep.
functor from C to set. It maps objects to sets. In fact, it's a contravariant functor, and I remember this not being hard to understand. So one functor C prime maps C prime to the set C. To define the action of this functor on F, we have to define the corresponding mapping between C and DC using non-capital C, and this other C, which is using C prime.
Little C prime.
So this is a functor between two sets.
Yep.
So one functor goes from C to set, and the other functor goes from C to C. But these two C's are not the same category.
From C to set. Yeah, it maps the cone to the home set of that cone to the yeah.
I'm
It's a
having a hard
functor.
time understanding what is the second functor though. So let's pick one
Uh,
element u of C and see if you can map it to some element here. An element
oh, the
of a home.
second.
Go.
I think the second one actually is the because this is contravariant. Like we're not going directly to the place that we want to be. We're going there to an extra step because we have to go to the opposite category, right?
Yeah. So one functor is the mapping. It's a functor from C to set. That's fine. Our functor maps that to define its functor. Blah blah blah. Yeah, we are still talking about only one functor here. This is only one functor. All of this. So let's pick one element u from this and see if we can map it to some other element there. So the answer is an element of the home set is a morphism, which makes sense, right? The home set is a set of morphisms. So if you
Yep.
pick one element of that, we have actually a bridge, right? We have a function. If you precompose u with f, we can actually acquire c prime to lim d. And that's an element there. So we have a mapping of morphisms. And this is the implementation, which makes a lot of sense. Oh, so now we go to the second functor. Now it makes sense. which is also from C to set, but this time we consider a set of cones. Cones are just natural transformations, so we are looking at the set of natural transformations. The mapping from C to this particular set is also a contravariant functor. So the two functors that you're going to bridge with a natural transformation, they are both contravariant.
Yep.
Cool. Wait a moment. The first functor happened in when bridging C to set, but C we are mapping objects. We're mapping objects to to sets of morphisms. Is that right? I think that's right.
Uh,
Yes.
yeah, it's the
One
mapping
functor
of
is the
C.
mapping of C to the set, but to this specific set, which is a set for some object C that goes to it's the set of morphisms that pick an element C and go to lim D.
Yep.
Cool. And this other one is also from C to set, but this one is from objects to sets of cones.
Oh, right. This is actually the set of natural transformations where the natural transformations that we care about are the ones that we just saw that were used to define a cone,
No,
right?
yeah, but there is a set of those. This is
So
getting
yes, because
way too
it's because
abstract.
we're not dealing with a single cone anymore. We're dealing with like general cones, plural. Like that's why it's a set.
Okay, so the first functor is from objects, the category of objects, to the category of sets of morphisms between a given C and lim D. Yes, I can picture that. And the other one is also from C to set, but from objects from C to sets of cones. But the problem is that a cone is actually a natural transformation, so it's a set of natural transformations.
Yep.
Okay, I see. Uh, how can we show that? So let's suppose that we have, let's define its section on a morphism, so we have F. And then here comes the crazy part. This doesn't have a name, but this is what I said. We're gonna do the lifting of F should be a mapping of natural transformations between two functors that go from I to C.
Yep.
Wait, two functors?
Yes, because when we define the cone, we use two functors to define the cone, right?
Oh, those ones. Okay, this could be better written then. How do we map natural transformations? Every natural transformation is a selection of morphisms, its components. One morphism per element of I. A component of some alpha, a member of the set of natural transformations. Oh, actually, I said it wrong. This is not this notation is already using the same terminology as before, so it's well written. It's my fault because this is the same delta C from all the way up there, and this is the same D as well. So these are the two functors, but I think the text should also say that. Cool,
Yep.
cool. Because this is basically mapping a cone to another one. Cool.
Yes.
So alpha. So the whole component thing is when you apply an element, right, of the category that the functor is
Of
doing
the
the.
Yeah, it's an element of the natural transformation at a particular point, I guess you could
Yeah.
call it.
Or using the constant functor, we can rewrite it as this. Given f and alpha, we have to construct a beta, a member of net. Its component at A should be a morphism this, but it's also using the delta, the constant functor trick. So it can be written as
Yep.
this. We can easily get the latter from the former by precomposing it with f.
Which goes from C prime to C, right? Because we have a delta C to a delta C prime in the component.
That's
In
the
the
thing, man.
sources,
That's the thing. I forgot what is C and C prime. I remember what I know what these are, and I know what is this, but I don't
C and
remember
C
what is
prime,
C and C prime.
those are the apices of the cones.
These are the apexes of the cones.
Yes.
I see.
Yeah, we have been
I
consistently using little c to refer to the top of a cone, and we're using c prime to refer to the top of a different cone. But
I see. And why do we want to map the apexes of the cones in this particular case?
because we need to be able to,
Oh, no, no, no. This
well,
is not the apexes of the cones. This is not the only one of them is. The other one is coming from this other guy, which is any object in the C category. The other C is coming because we are describing cones, and as you said, we can describe cones only by the apexes. So the this is actually mapping an object from C to the representative of the object of set. And this is basically fmap then, but that's going to be contravent. So this is contramap.
yes, this is contramap.
There's no implementation here. How cool. How freaking cool. Let's go up a little bit. Yeah, here this one has one. It has the implementation.
It's literally just a backwards composition.
Oh no, yeah, I remember that. You could just do flip dot, and that's it. Um,
This actually reminds me of the implementation of contramap for
yeah,
functions, actually,
yeah, the
which
reader,
this
right?
kind of is, right? Yeah.
Okay, I see. Okay. Whew. Okay. We can easily get the letter from the former by recomposing. Yes. Now that's the easy part. Once you get all these types on the table, it's just Tetris, and it's just okay. And here's the drawing of that, right? Here's the drawing of that.
This
But
mapping
that's
defines contramap for the functor, and the functor is this thing.
wait. I don't know if I said bullshit now. Did I say bullshit? Is this not? Are those actually both apexes of the cone and not from these things? Or am I mistaken?
Uh,
Because somewhere in this process there needs to be elements. It's saying here we are mapping objects from C to the set of cones. Where are we mapping the objects from C? My understanding it needs to be this, or am I mistaken?
yeah, I think it's that actually. Because like we're trying to find the lim D, right? That's the
Yeah,
whole point of this.
yeah. So let's just move on. Given our amorphism F, we have just built a mapping between two natural transformations component-wise. No, man, this needs to be what you said. Both are apexes of cones. So I don't really understand. How are
But a
we
cone is
mapping?
it's because a cone is defined by a natural transformation.
No, I understand that part. What I don't understand is we need another functor that's also do a mapping from C to set. But this time we consider the set of cones. Cones are just natural transformations. The mapping from C to this particular set is a contravariant. C is an object from this other C, agree?
Yes.
So where are we doing that?
Mapping
Am
from
I
C.
wrong? Am I confused?
They may both be confused actually.
Like, am I saying nonsense? Like, maybe I am. Maybe I am. because the diagram from the first one is also not is also doing that. See.
One functor is the mapping of C. Oh, C is actually a parameter, actually. It's abstract. It's a type variable.
I think it's no. I think now I think we are correct. The C prime is actually from this capital C here, but I don't really understand. Maybe no, but it's saying F. F. Given our morphism F, we have just thus built a mapping between two natural transformations. How? If that needs to mean that these two are apexes, right?
If you scroll down a little bit, you can actually see that in the diagram on the next page. You see the C prime and the C are apices of cones, and here we're interested about a particular node at the base, right, which is called DA,
Mm-hmm.
and and
Oh, wait.
and beta and alpha are natural transformations between the functor that goes from I to C and C prime, and also and the D that actually goes to the base.
Mm. Okay, wait. So then this F is not a functor as well. Where is the other functor to make beta and alpha here? Oh, it's the constant.
It's the constant
Oh,
ones,
it's
yes,
also being coming from I to this one then.
yes.
Why that's not written
I have no
here?
clue.
Okay. This mapping defines a control map for the functor. So this is basically doing, this is mapping an object to a cone, which is an natural transformation. What I have just done is to show that we have two contravariant functors from C to set. um, so there is
I
a
have
name for contravariant functors from any category C to set. I don't know how to pronounce that though. Pre-heaves?
no pre-sheaves actually.
Pre-sheaves. Pre-sheaf. Pre-sheaves. Now that we have two functors, we can talk about natural transformations between them. So without further ado, here's the conclusion. A functor d from I to c has a limit d if and only if there is a natural transformation between the two functors I have just defined.
Not just a natural transformation, but actually a natural isomorphism. So it needs to be
Natural, I
invertible.
read it wrong. Natural isomorphism. You're right. You are 100% right on that. So this is a functor and this is a functor. That's what it's saying?
Uh,
That's kind of
Functor
confusing.
D has a limit lim D if and only if there is a
Oh, it's
natural
no, 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 no.
isomorphism.
It's
Oh,
confusing. It's because both of those have the common factor of going from C to them.
yeah.
This is applied to both, but it's being removed by notation for some random reason. Um, let's remind what natural isomorphism is. It's a natural transformation whose every component is an isomorphism. That is to say, an invertible morphism. I don't know if I understand what that means. When dealing with natural transformations, you usually focus on components, which are morphisms. In this case, since the target of both functors is set, the components of the natural isomorphism will be functions. Um, sure. These are higher order functions because they go from the home set to the set of natural transformations. Wait a moment.
Right, because you go from the home set C, big C, from little c to lim D, to and back the home sets of the natural transformations between um,
Ah, I see, I
delta
see, I see, I
C
see, I see.
and
It's
big
because
D.
the target of the functor is set, and in particular the set of morphisms.
Yes.
So it is a higher order function, which is very hard to see, but now I see. You can analyze a function by considering what it does to its argument. Here the argument would be a morphism. Here the argument would be a morphism. Uh, Wait a moment.
Right,
When
because it's a
dealing with
higher order function, so it naturally takes an argument which is itself, well, in this case, it's a morphism, right?
oh the component of the natural transformation alpha or beta things, the a and the b or the letters that we use to fix the component, those are functions now. Is that right?
Oh, yes, that seems
Sure,
right.
sure. Uh huh.
Yeah, this is actually
Uh huh.
reading this chapter, like I found it way easier to follow what's going on when there were diagrams actually. The and this may be true, this may be true of category theory in general, but yeah, diagrams help a lot.
Like, because that's what I'm trying to do by myself. I'm trying to draw them in my mind.
Yeah.
Uh, the most important result is that neutrality condition for this is exactly the commutativity condition. Uh, uh, as a preview of coming attractions, let me mention that the set this can be thought of a home set in the functor category. So our natural isomorphism relates two home sets, which
Which
points
points
at
at
even
an
more
even
general
more
relationship
general.
called an adjunction.
I have heard that name before, and I'm not entirely sure what it means, but it is important.
But it is important. Cool. Um,
And then there are more examples of limits.
yeah. Which none of them are obvious, by the way. I don't know. I found this one pretty interesting, by the way. These two. But let's go through them. Um, so there is even a simpler example of a limit, the terminal object. The first impulse would be to think of a singleton category as leading to a terminal object, but the truth is even starker than that. The terminal object is a limit generated by an empty category. The terminal object is a limit generated by an empty category.
Right, because you need to map the category to an object in another category, right?
Yes,
Well,
yes,
not
if I
really,
follow.
not really the category, because like there are no objects inside of the category because it's empty, right?
Yeah,
Really, every functor from that to another category will be a constant functor, right?
yes, also yes.
And then if you apply the limit, this whole limit thing that we saw earlier to that, then by definition you get the terminal object because, well, to be a limit, it needs to have a single morphism from every object to itself, right?
Yes.
And that's what you kind of generate when you take the limit.
Yeah, but it's written weird. A functor from an empty category. So the functor is coming from the empty, not going to the empty. A
Yes.
functor from an empty category selects no object. So a cone shrinks to just the apex. Where is the apex? Is it in the other category?
Yes, it is in the
Ah,
target.
the universal cone is the lone apex that has a unique morphism coming to it from any other apex. You recognize this as the definition of the terminal object. I guess. The next interesting limit is called the equalizer. It's a limit generated by a two element category with two parallel morphisms going between them. It's a limit generated by a two element category with two parallel morphisms going between them. This category selects a diagram in C consisting of two objects A and B and two morphisms. To build a cone over the diagram, we have to add the apex C and the two
into
projections.
projection.
Why is this called equalizer though?
We're getting to that. This is actually kind of interesting.
It's a limit generated by a two element category, so the two elements are A and B, I suppose.
And there are specifically two morphisms that go
Yeah,
between
it's a
them in
very
parallel.
okay, like this is definitely a cone. And in reading this, you can actually see commutativity again. So this should be equivalent of doing this, and this should also be equivalent to doing this, which is exactly
Yes.
what is written here. So this tells us that Q is uniquely determined by one of these equations, say this one, and you can omit it from the picture. So then we're gonna try to make, oh, so if this is equal to this, let's say that, let's make this equality and say F after P should be equal to G after P. And there is a very interesting interpretation of this, which is that if we restrict our attention to set after the function, the image of the function P selects a subset of A. Uh,
And when restricted to this subset, the functions f and g are equal.
so this is basically saying that once you restrict the domain by applying P, you can say that f and g are the same thing. So for instance, take A to be the two-dimensional plane parameterized by the coordinates x and y. Take B to be the real line and take. So so here's how you interpret this. We are basically trying to say that f is equal to g if we pass through P first. What that means? That means, in fact, we can derive P. That's something that I felt that he should have said before showing the answer. We can derive P ourselves because it's just a matter of equalizing F and G. This will tell us what P should be. And I did this exercise myself. So if you pick this thing and put it equal to this, and put y in one side and x in the other side, and rename x to be t, you're gonna see that x becomes t, and the image is gonna be exactly what the equation follows. And I thought that he should have said that. Did you follow, Marin?
Yeah.
So if you pick this and put equal to this, you're gonna see that y is equal to minus 2x, minus
And then you just
2x,
relabel x
and you
to t.
label x to t, and then it's gonna be an f of x equals to x. But we are calling in here p, and we also return x for some random reason. Then that's gonna be the image. Notice that pt defines a straight line in the two-dimensional array. Along this line, the two functions are equal. And of course they are, because the image will coincide, because we are basically saying that they are equal in like algebraic terms, like if you put this equal to this. Of course, there are other sets C prime and functions P prime that may lead to the equality, but they are all uniquely factored out through P. So what we are basically saying, is there another P prime that can hold this property? And the answer is yes, but they can be
It's
factored
not
out through P.
universal. Yeah, it's not universal.
Um, so let's suppose that we have this P here. It's a good cone because this is equals to this, but it's not universal because of the unique factorization through H, right? So this is the same trick that we use to define products and coproducts. It's exactly the same, and by extension, the same trick that we use to define limits. Um, which is what I just said. So he just said it, but not up here, down here. It's much more general because it's defined in terms of objects and morphisms rather than algebraically. An even more general idea of solving an equation is embodied in another limit, the pullback. Here, we still have two morphisms that we want to equate, but this time the domains are different. We start with the three object category of the shape this. The diagram corresponding to this category consists of three objects with the three object category of the shape. Sure. This diagram is often called a cospan. Is that how you pronounce that? I believe so. Marinho, you are muted.
I was muted. Yes. It's a co-span because it's a span, except we reverse the direction, so it's the co-span.
Wait, repeat that.
It's a co-span, not a cospan, because it's a span. Like if you get rid of the co, it's just a span,
It's a span.
but we but it's the dual of a span, so it's actually a co-span.
Ah. So commutativity conditions tell us that R is completely determined by the other morphisms and can be omitted from the picture. So R can be omitted. R can be omitted, and then we say, yep. Um, so there are only so we are only left with the following conditions. A pullback is a universal cone of this shape. This is the factorization.
Yep.
I see. There's also co-limits coming in. Yeah, man, we are very screwed.
Yeah,
Very screwed.
co-limits are basically like limits, except you reverse all the arrows and you just
Yeah.
follow the same line of reasoning.
If you narrow your focus down to sets, you can think of the object D as consisting of pairs of elements, one for which F acting on the first component is equal to G acting on the second. F is acting on the first,
Which is A,
and G is acting on the second.
which is C
If this is
in
too
this
general,
diagram.
consider a special case in which G is a constant function. Then you are really solving this equation. Yes. Yeah, but this special case has a very trivial solution because C is irrelevant. Uh, the set A could, for instance, be the set of three-dimensional vectors, and F the vector length. Then the pullback is the set of pairs V and unit, where V is a vector of length 1, 2, 3. Wait, why is this the case?
Because we're assuming that C is the unit type and G is a constant function, and you're basically saying, okay, F is the vector length, so it takes a vector, returns the length, which,
Mm-hmm.
evil square roots, but okay.
That's fair.
And then, because of the diagram, you have this equation which tells you that, hey, this evil square root of, the squares of the components needs to be equal to the output of G applied to the units. So there's only one possible value, which we just established is 1.23.
Mm. The set A, F. But why is this on a pair? That's what I don't follow. Oh, because that's how we define it via the P thing. Across the P line, the image are the same. So let's say across the V line, the image is the same.
Yeah, here it's giving the example that, okay,
Uh,
the set A is, in this case, as an example, is a three-dimensional vector, and then the pullback is actually it's actually a pair because if you go up a little bit back to the diagram, the pullback is actually you need the A and the C together because you need to have F and G defined, right?
yeah, the only part for me that's confusing is the unit. Why do we need the unit? The unit should be the image, no?
No, the unit is actually the input to G, which we just said is a constant function, right? We need a dummy type to give it, so we just chose the unit because it's it's only ever going to return one possible value, so no reason giving it
Oh, I'm stupid. That's correct. That's 100% correct. Then we go talking about inheritance. So I'm not going to read all of
inheritance.
this, but it's basically using an example of how this diagram can be useful to understand inheritance in C++.
Yes.
That's basically what it's saying. So it's a very similar diagram here, which is cool, which is very cool.
Yeah, it was slightly unexpected, but it is very cool.
Yeah. Then we have the example of pullback in the sense of type inference for unifying types of two expressions. So there's many algorithms to do this though, and he is very clever to not describe them because that would be 100% beyond the scope. But
Yeah,
you can look at at this diagram up here and use it to understand how this type inference works, right?
right.
Then we have just the
And it-
colimits, which is basically reversing all the arrows that we just saw before.
yeah, this whole thing about okay, you get one, you get one, and you get another one for free. That's actually very convenient because you only need to understand half the book actually.
Yeah, but this is not really a cocone though, because it's the same thing but upside down, no?
Yes, it is a cone because it's the opposite of a cone. So
But it isn't the opposite. That's my understanding. It's just this.
yeah, you just you take the normal image, the normal diagram of a cone, and you just flip all the arrows, and then for visual symmetry, I guess, you also turn it upside down.
Yeah, it's basically rotation on top of the product, the co-product.
Yeah,
Cool. And now we go to the definition. Is this the last one? Yeah, this is the last one.
it
We're
is.
really out of time though, but let's go. We go to the understanding of continuity, right? So I said previously that functors come close to the idea of continuous mappings of categories in the sense that they never break existing connections. So now we're gonna define what is a continuous functor, which is the one that preserves limits.
Yes, not just connections, but also limits.
Every diagram D in C can be mapped to a diagram applying the functor by simply composing two functors. The continuity condition for F states that if the diagram D has a limit D, lim D, then the functor also has a limit which is equal to applying the functor to the limit also. This picture is kind of not good in my opinion.
It's very not good.
Yeah, because it's not really showing the guts well of the limit being there and being transposed. But okay.
Notice that because functors map morphisms to morphisms and compositions to compositions, an image of a cone is always a cone. That's actually kind of interesting, but
A commuting triangle is always mapped to a commuting triangle. Functors preserve composition, obviously. The same is true for factorizing morphisms. The image of a factorizing morphism is also a factorizing morphism. So every functor is almost continuous. What will go maybe wrong is the uniqueness condition. The factorizing morphism in C prime might not be unique. There may also be other better cones in C prime.
they are not available in C.
Oh, that follows because maybe the other category that you're going is it has more stuff. Just that. It
Yes.
has more stuff. And if that's the case, uh, you cannot map all the elements of the first category into the second one because the thing needs to be unique, which basically means that we're gonna have some things hanging on the other category, and those things hanging may compose and create a better cone.
Yes.
So yeah, a home functor is an example of a continuous functor. Recall that a home functor is a contravariant in the first variable and covariant in the second. In other words, it's a functor this. What is COP again? I keep forgetting.
It's the opposite.
No. When its second argument is fixed, the home set functor, which becomes representable per sheaf, map co-limits in C to limits in set. And when its first argument is fixed, it maps limits to limits. I don't remember this home functor thing. Do you remember that from before?
It's kind of like a home set, but it's between categories.
I don't. Oh yeah, no, yeah, of course, because that's what functors are. So this is actually the Cartesian product of all the functors between these two things.
It's the set of all the functors between those two things, yes. Well, I think so. I maybe misremembering actually.
But that's the notation for Cartesian product, no? Am I wrong?
The home functor is contravariant in the first variable and covariant in the second.
No, not that
Right, because
notation. This one.
yes, because yeah, it actually takes like two, I guess you could call it arguments, I suppose. You know how function types have a higher kind? It's that basically because you
Hmm.
have an input and an output, not just whatever.
Wait. Function types have higher kind, you said.
Well, yes, because they
They
take
have
two
higher
type
kind. I don't.
parameters.
So I just don't understand what the how this connects to this.
Because a functor, it has like it has a beginning and an end, right? An input and an output because it's a transformation between two categories, right?
Sure.
The source and the target.
Sure.
And it's basically saying um, yeah, the first variable, I guess, of this functor that goes from A to B in this example, it is contravariant, and the other one is covariant because that's how arrows work, man. I guess.
That's cool. A home functor is the mapping of any two types to a function type. So it's just a parameterized function type. When we fix the second parameter, let's say to string, we get the contravariant functor. That I know. Continuity means that when toString is applied to a colimit, for instance a coproduct either BC, it will produce a limit, in this case a product of two function types. Hmm.
Indeed, any function of either BC is implemented as a case statement with the two cases being serviced by a pair of functions, right? One from B and one from C.
Hmm. I still really don't understand this notation on the top because this is Cartesian project product notation, but it isn't the Cartesian product then.
I mean, no.
So I don't understand the notation at all.
I think this is to avoid having two arrows, I guess. Because that would be the more usual way to do this in a Haskell-like notation, right?
I think so. Hard to tell. Hard to tell. Similarly, when we fix the first argument of the home set, we get the familiar reader functor. Its continuity means that, for instance, any function returning a product is equivalent to a product of functions. I don't know if I understood this, man. This whole home functor thing. Hmm. I may have to revisit this. You don't need the category C to figure these things out. And you're right. But we did that without using any computer abstractions at all. And then there's the inspiration of the terminology, which is coming from calculus, not surprisingly at all. So I don't know if I understood this, man. I really don't. Could you try
Yeah,
to
I've got
give me another shot? Like we have 2 minutes. So do you have any other way to explain this? Hmm.
a home functor. Home functor. Man, it's been so long, I kind of forgot what a home functor is supposed to be, actually.
That's cool. Is the mapping of two types to a function type. In Haskell, a home functor is the mapping of any two types to a function type. Okay, so what are the two types in the first example?
They are the arguments type and the return type.
So A and string.
Yes.
And in the other example is gonna be um, the first argument. So R to whatever. R to A, in this case tuple,
When we fix the first argument, that means we're fixing the input type.
which is R.
We get, which is R, yes.
We get the reader functor, which is correct. This could be anything. In this case, we're using a tuple just for simplicity, I believe.
Its continuity means that, for instance, any function returning a product is equivalent to a product of functions. Right, because you could have a function that goes from
It
R to A and another
it
that goes from R to
it
B, and you
feels
can
like
just.
distributivity though, because look, these seem like visually it's grabbing a B going to string and grabbing a C and going to string, and this one is doing the distributivity again, but from R going to A and R going to B.
Yeah, kind of. The reason in the top case we're going from either to a pair
It's because it's
product,
covariant.
because it's contravariant in that case,
Yeah.
yes.
Oh, I said it wrong. Contravariant. You're right. Hmm. I think I'm starting to see. This notation is really not helping me though. But that's okay. I think I need to digest a little bit more, but that's okay. I think I got the main idea. That's the end. So next time, free monoids.
The home functor. Um, Mapping detects a pair of objects A and B and assigns to it the set of morphisms between them. The home set C from A to B is a functor. Oh, right, it's basically the combination of the reader and the op. The examples for flow and
Mm.
contravariance.
So it's a combination of the reader and the op. I remember that.
Yeah, it's basically the arrow type constructor.
Mm. Okay. Oh, so that's why it's saying parameterized function type.
Yes.
Okay. Cool. Do you have anything else to say? I'm gonna finish the recording now.
You missed the pun on my name.
On your name.
Yeah, remember when I said little c, and then later you were about to say something that would result in you saying little c, and I said myself.
Really? That's weird.
Yeah, it's because little c, as in the letter C, is pronounced the same as little c, as in a small body of water, which is an ocean, but not really because it's just a sea, which is marinho.
That was terrible. Terrible.
It's not my fault though. I actually borrowed it from
It
a
is
friend who
100% your
came up
fault.
with
I'm
it.
gonna finish the recording now.